An object from another star system is passing through our solar system right now, and for 6 weeks, we had no idea if it was still alive. Since July, astronomers have been tracking 3I Atlas, a visitor from beyond our solar system, moving through space with a velocity that no object born here could possess. For months, the instruments pointed, the data accumulated. A picture, incomplete but extraordinary, began to form. Then in October, it vanished. Not into darkness, into light. As 3I Atlas swung toward its closest approach to the Sun, perihelion, it slipped behind our star from Earth's perspective, and the ground-based telescopes that had been its steadiest observers went effectively blind. The timing could not have been worse. The comet was now close enough to the Sun to be at its most active, most luminous, most chemically volatile. The very moment scientists had waited months to observe was happening on the other side of an 800,000-mile wall of plasma. This is a story of what happened during those weeks, what the Sun hid and what other instruments, scattered across the inner solar system and beyond, quietly recorded. Before 3I Atlas disappeared from Earth's view, it had already issued a warning that it was not a straightforward object. In late August and September, NASA's Swift Observatory, a satellite ordinarily tasked with detecting gamma-ray bursts, turned its ultraviolet instruments toward the approaching comet. Swift's UV sensitivity allows it to detect hydroxyl radicals, the molecular fragments produced when sunlight breaks apart water molecules. The detection it returned was striking. At 2.9 astronomical units from the Sun, nearly 3 times the Earth-Sun distance, a region where temperatures remain deeply sub-zero, 3I Atlas was releasing water at a rate of 40 kilograms per second. The analogy is not elegant, but it is accurate. The equivalent of a fire hose at full pressure, running continuously at a distance where water ice should not yet be sublimating with anything like this intensity. Standard cometary models predict that water ice becomes aggressively active only as an object draws inside roughly 2 AU from the Sun. At 2.9 AU, this rate of outgassing implied something beyond simple surface sublimation. The leading interpretation was that 3I Atlas was ejecting fine icy grains into its surrounding coma, a cloud of gas and dust that envelops the nucleus, where those grains would melt independently, vastly multiplying the effective surface area available for sublimation. It was, in other words, not behaving like a comet that was warming up. It was behaving like one already in full eruption. Then it rounded the Sun, and Earth's telescopes lost it. The gap in ground-based coverage was not total. A network of spacecraft orbiting at different positions around the Sun, instruments designed for watching solar weather rather than comets, had lines of sight that Earth did not. A study led by Qi-Cheng Zhang of Lowell Observatory and Carl Battams of the U.S. Naval Research Laboratory drew on data from 3 of these platforms: Stereo A, the SHO satellite, and the recently launched GOES-19. Each uses a coronagraph, a disk that blocks the Sun's direct glare, creating an artificial eclipse, to observe the solar environment. In October, these instruments turned their attention to 3I Atlas. What they recorded was a comet in the middle of a transformation. For months, 3I Atlas had been brightening at a rate that astronomers express as a function of distance from the Sun, specifically as a power of that distance, designated R. Before October, the brightening scaled at approximately R to the negative 3.8, a respectable figure indicating steady, active sublimation. Once the comet passed inside 2 AU, that exponent shifted dramatically. The new measurements showed a scaling of R to the negative 7.5. To understand what that means, brightness was no longer increasing in proportion to proximity. It was accelerating. Mass was being shed at a rate that conventional models for volatile-rich comets struggle to accommodate. The comet was not simply warming. It was, in some meaningful sense, opening up. The color of the coma confirmed this. For months, observers had seen 3I Atlas as red, consistent with dusty, organic-rich outer surfaces like those inferred on the first known interstellar object, Oumuamua. Then it shifted to green, a signature of diatomic carbon and cyanogen emissions as it was warming. But through the LASCO and CCOR1 coronagraph filters, Zhang and Badams reported something else. The coma appeared distinctly blue. Blue in cometary spectroscopy is the signature of gas fluorescence, specifically carbon monoxide and amide radicals. The interpretation is that as the comet reached perihelion, the intense solar radiation burned through its outer dust-laden layer. The red crust, accumulated material from an unknown star system carried across interstellar space, peeled away. What emerged beneath was a chemically distinct interior, a wet, volatile engine that had been waiting, insulated, for the right conditions to reveal itself. The color sequence tells a story. Red on the outside, green in transition, blue at the core. The comet was undressing, layer by layer, as it passed through the sun's heat. Just before perihelion, 3I Atlas passed within 0.19 AU of Mars, approximately 28 million kilometers. This was a coincidence of orbital geometry that planetary scientists received as an unexpected gift. An entire fleet of robotic instruments at Mars was in a position to observe. NASA's Mars Reconnaissance Orbiter swiveled its HiRISE camera toward the comet. HiRISE is capable of resolving objects roughly the size of a dining table on the Martian surface from orbit. It was, in theory, the instrument most likely to return a resolved image of the comet's nucleus. The images were delayed weeks by the US government shutdown, a gap that generated its own set of speculations about what might be withheld. What NASA eventually released was, in practical terms, a non-detection. A fuzzy, unresolved spot embedded in a cloud of gas and dust roughly 1,500 kilometers across. The nucleus, almost certainly no wider than 2.8 kilometers based on Hubble Space Telescope measurements, remained hidden inside its own atmosphere. The image resolved nothing about the shape or surface of the object at its center. This non-detection is, however, scientifically useful. The size of the enshrouding coma relative to the estimated size of the nucleus gives researchers constraints on the mass loss rate. A smaller object producing a larger coma implies a higher ratio of outgassed material to remaining solid mass. ESA's Mars Express and ExoMars Trace Gas Orbiter also imaged the comet during this period. NASA's MAVEN satellite used its ultraviolet spectrograph to map a hydrogen envelope extending far beyond the visible coma, a vast, tenuous cloud marking the outer boundary of the comet's influence. And then there was Perseverance. The rover, positioned in Jezero Crater and currently in the midst of a geological investigation that has returned what may be biosignature evidence in ancient sedimentary rock, pointed its Mastcam-Z camera upward into the Martian night sky. The resulting long-exposure frames show 3I Atlas as a faint smudge drifting among fixed stars, barely distinguishable, easily missed. The scientific content of those images is minimal. Their significance is of a different order. It is the first time in the history of astronomy that an interstellar object has been photographed from the surface of another world. A camera on a rover on Mars captured the light of something that did not originate in this solar system. That fact sits quietly in the data, without fanfare. As 3I Atlas emerged from behind the sun in November, the astronomical community found itself in an unexpectedly anxious moment. Harvard astrophysicist Avi Loeb, who had been publishing a series of detailed analyses of the comet, suggested that 3I Atlas had fragmented, that the brightness surge had been so extreme as to imply the nucleus had broken apart into at least 16 pieces. His reasoning was grounded in mass loss calculations. If the comet was shedding material at the rate the brightness curves implied, the nucleus might simply have dissolved. Subsequent observations from the Lowell Observatory and the Virtual Telescope project resolved the question. Astronomer Zhang reported the comet appearing structurally intact, no fragmentation train, no debris field, no dispersing remnants. The nucleus survived. The extreme brightness event was a period of intense surface activity. the shedding of an outer crust under intense solar heating, not the disintegration of the body beneath it. Loeb's fragmentation hypothesis was not his first extraordinary claim about 3I Atlas. Over preceding months, he had published a sequence of articles arguing that the comet's behavior showed features consistent with artificial propulsion. He pointed to two specific observations: a jet of material appearing to shoot toward the sun rather than away from it, and what he described as non-gravitational acceleration, a deviation from the trajectory predicted by gravity alone, that he argued could not be explained by natural outgassing without destroying the object. These claims received significant public attention. They merit examination on their scientific merits. The sunward jet is real. Images from the 2-meter twin telescope at Teide Observatory in the Canary Islands, a composite of 159 individual exposures taken in August, show a clear asymmetry in the coma, material extending not just away from the sun but toward it. This feature, however, is not unusual in cometary science. As a comet's sunward hemisphere heats preferentially, sublimating gases can escape through weak points in the crust in directions that are not purely anti-solar. The solar wind then acts on this material, bending and fanning it, creating structures that, from particular viewing angles, can appear to point directly at the sun. Comparable features have been documented in Comet Halley, Comet Neowise, and the extensively studied 67P Churyumov of Gerasimenko. There is nothing in the geometry of a sunward jet that requires a non-natural explanation. The non-gravitational acceleration is also real and also explicable. A new dynamical study by Goldie Ahuja and Shashi Kiran Ganesh modeled 3I Atlas's trajectory across a simulated history of roughly a century, incorporating the measured outgassing rates. Their result, the observed deviation from purely gravitational motion, is fully consistent with the thrust generated by the water and carbon dioxide loss already documented by Swift and other instruments. The comet is losing mass at a high rate, but the survival of the nucleus indicates that the body is structurally robust, not that it is light, hollow, or propelled. Loeb's intuition that an object losing mass at this rate should not survive intact is precisely what makes the MeerKAT results significant. The MeerKAT radio telescope array in South Africa, an instrument of remarkable sensitivity, consisting of 64 dishes spread across the Karoo Plateau, detected a faint signal from 3I Atlas at two specific frequencies, 1,665 and 1,667 MHz. These are the known spectral lines of the hydroxyl radical in radio emission. Hydroxyl, the OH molecule, is a direct product of water ice sublimating under ultraviolet radiation. Radio waves penetrate gas clouds that scatter and absorb optical light, allowing instruments like MeerKAT to effectively look through the coma and measure gas density directly, without the ambiguities introduced by dust. The detection confirmed what Swift had implied months earlier. 3I Atlas contains water, and a great deal of it. This is the first time radio emissions have been detected from an interstellar object. The implication for the artificial propulsion hypothesis is unambiguous. A spacecraft, whether a decommissioned probe, an alien vessel, or any other dry metallic structure, does not emit hydroxyl lines. The hydroxyl signal is produced by photodissociation of water ice. You cannot fake it with technology. If the signal is there, the water is there. And if the water is there, the object is a natural icy body. The MeerKAT detection does not merely weigh in on one side of the debate, it closes it at the chemical level. 3I Atlas is a comet. The confirmation that 3I Atlas is a natural object does not diminish its scientific interest. In some respects, it amplifies it. A paper by Romain Macchiolo from the Royal Belgian Institute for Space Aeronomy, drawing on observations from the James Webb Space Telescope and the SPHRX mission, addresses a ratio that had puzzled researchers since early observations: the extraordinary abundance of carbon dioxide relative to water. In typical solar system comets, CO2 constitutes roughly 12% of the water content by abundance. In 3I Atlas, that ratio is approximately 7.6, meaning carbon dioxide is present at nearly 60 times the expected proportion relative to water. The comet is not merely enriched in CO2, it is overwhelmingly dominated by it. Maggiolo's proposed explanation involves a process that operates on timescales that are difficult to conceptualize: galactic cosmic ray bombardment over billions of years. As 3I Atlas drifted through interstellar space, it was continuously exposed to high-energy particles originating from supernovae and active galactic nuclei, the most energetic events in the observable universe. These particles penetrate solid matter to depths of 15 to 20 meters. When they interact with molecular bonds in ice, they break them. Over billions of years, this process converts carbon monoxide and water ice into carbon dioxide and complex organic compounds. The result is a chemically processed outer layer, a radiation crust that extends tens of meters into the comet's surface. What we are observing when we study 3I Atlas is not the primordial interior of this object. We are watching its galactic sunburn peel away. The CO2-rich coma is not a window into the comet's original composition. It is the residue of billions of years of interstellar irradiation. This has a broader implication that Maggiolo's paper does not understate. Any interstellar object that has spent the geologically significant time in the void will look like this. The assumption of pristine preservation, the idea that interstellar visitors are perfect time capsules of their origin systems, may be fundamentally wrong. To see an unaltered interstellar object, we would need to catch one that is very young, or wait for one to fragment catastrophically and expose its unirradiated core. 3I Atlas has been cooking for a very long time. There is one more chemical surprise. Josep Trigo Rodriguez and colleagues compared the light spectrum of 3I Atlas to the spectra of meteorite classes found on Earth. The closest match was to Cr carbonaceous chondrites, among the most primitive meteorite types, distinguished by the presence of fine iron and nickel metal grains embedded in their matrix. Consistent with this, observations from the UVES spectrograph at the Very Large Telescope in Chile detected nickel and iron vapor in the coma's coma, with a nickel-to-iron ratio notably higher than any solar system comet previously observed, including the 2019 interstellar visitor 2I Borisov. The ratio declined as the comet approached the Sun, suggesting chemical processing was altering the relative abundances, and the VLT team noted that at these rates, the comet's elemental signature may eventually become indistinguishable from solar system objects. The presence of metals inside the comet may explain some of its more dramatic behavior. When liquid or high-pressure water comes into contact with iron and nickel under the right conditions, it can drive Fischer-Tropsch reactions, exothermic chemical processes that release heat. In a porous, icy body, that heat melts additional ice, which contacts more metal, releasing more heat, building pressure beneath the crust until the crust ruptures and a jet of gas and dust erupts outward. This mechanism, a form of cryovolcanism triggered by metal-catalyzed chemistry, provides a natural account of the brightness surges, the jets, and the rapid mass loss, without requiring any extraordinary hypothesis. As of late 2025, 3I Atlas is outbound. It has survived perihelion, altered but intact. The surface that began this journey is mostly gone now, sublimated, blown away, transformed by the sun's heat into the coma that spread across 1,000 kilometers of space. Whatever the comet looks like today, it is not what it was when it entered the solar system. On the 16th of March 2026, 3I Atlas will pass approximately 0.35 AU from Jupiter, moving through the planet's Hill sphere, the gravitational domain where Jupiter's pole dominates over the Sun's. The comet is moving far too quickly to be captured, but Jupiter's gravity will deflect its trajectory one final time, and the Juno spacecraft, currently in Jovian orbit, may be positioned to record one last observation before the comet exits the solar system permanently. After that, 3I Atlas returns to the interstellar medium. It will drift, irradiated, and diminished for perhaps billions of years before any other gravitational encounter. No instrument humanity currently possesses or is likely to possess within any foreseeable future can follow it. What the story of 3i Atlas leaves behind is not primarily answers. It is a recalibration of questions. We assumed interstellar objects would be pristine. They are not. They are processed by radiation over timescales that dwarf the age of anything we think of as ancient. We assumed the void between stars was simply absence. It is not. It is an environment, active, penetrating, chemically transformative, that leaves its mark on everything moving through it. We assumed an object bright enough to observe would be legible. 3i Atlas was bright enough to be seen by amateur telescopes. It was never at any point fully understood. A rock, if that word still serves, has traveled from another star system, carrying the chemical record of billions of years of galactic experience. It passed through our solar system in a matter of months. It is already leaving. There is nothing to announce here. The data is what it is. Water, carbon dioxide, hydroxyl lines, iron, nickel, cyanides, a surviving nucleus, a comet that is almost certainly exactly what the chemistry says it is. And still, quietly, something in the completeness of that explanation feels like the beginning of a much longer question.